We are discussing the various ways in which covariates can influence variable relationships. And continuing on with that theme, let's look at the idea of chain relationships. The relationship of x1 to y in this diagram here is through x2. x2 is called a mediator variable, and x2 becomes the explanation for the relationship of x1 and y. As an example, education influences income, which in turn influences length of life. Let's look at that another way. So imagine that it was observed that education has a nice strong correlation with length of life. So, of course, that's going to get people wondering, can we draw a straight arrow? Can we say that the more education one has, the longer they'll live? And if so, why is that? Well, we should always ask why. And when we start thinking about the why would education lead to longer life? One possible explanation is that there's a mediating variable. That is, there's an explanation, and that explanation is income. Because with more education, we would expect to see higher income. Education influences income. And income can influence length of life. Now, why? Why would that be? Well, there's other variables that we might want to put in here as well. Income is affecting the ability to obtain medical care. It's affecting how good the insurance is that you have that allows you to get care whenever you need it. Income might affect your ability to be able to go to the gym and exercise or eat a certain way. So there's many, many different variables that income might in turn be influencing, which in turn influences length of life. So you might think of, well, there's other mediators that we could put right in here that would explain the relationship of income to length of life. But I think we're a lot more ready to think about those kind of mediators once we've identified that income mediates the relationship between education and length of life. I actually have an entire video series that I'm going to do on mediation, and so that's all we'll say about this at this time. We've already talked about confounding variables and how confounding variables may lead to a spurious relationship. But it doesn't necessarily need to be the case that a confounding variable creates a spurious relationship. There might be a direct relationship as well as an indirect relationship of that variable. A spurious relationship would mean that there is no arrow between x2 and y. That is, the only reason x2 is related to y is because of x1. And that would be a spurious relationship. But sometimes you might have an arrow from x1 to y, an arrow from x1 to x2, and legitimately in its own right, x2 influences y, and some of the influence is indirectly affected by x1. Here's an example. Test anxiety may influence achievement on a test, both directly and through the influence on productive study time. So, drawing a picture of this, do we expect that study time could influence test performance? I hope you say the answer is yes, that study time should influence test performance. So that's a legitimate relationship here. The relationship that we observe between study time and test performance is not spurious. It's a real relationship. However, note that if we have someone with high test anxiety, that level of anxiety can affect their performance on the test directly, but it also might influence their study time. That is, they're not engaging in as much productive time studying because they're really spending a lot of time worrying about the test. One of the theories of cognition has information processing at the core, thinking of this in terms of a computer. And if you think of the mind as having limited resources, and a lot of those resources are being expended to be anxious, then that reduces the effectiveness of study on performance. So test anxiety can influence performance. It can also influence or inhibit performance because of inhibiting study, even though study of its own right will influence performance. So these relationships can be quite complex, and a confounding variable does not need to just create a spurious relationship, but it could be influencing the relationship among two variables with each other. One way in which this direct and indirect relationship could occur is that x1 could confound the relationship between x2 and y in such a way that it becomes a suppressor variable. That's really the opposite of spurious relationship, where a confounding variable creates the illusion there's a relationship that otherwise wouldn't be there. This is the opposite. There is a relationship among x2 and y, but x1's making it look non-existent or very small. As an example, suppose that academic achievement appears unrelated to job performance, but then we take into account the repetition of job tasks, and all of a sudden academic achievement is related to job performance. So another picture. So we have academic achievement, and we have job performance, and we look to see if there's a relationship here, and we find out, no, not much of one. Not much relationship. We might as well go ahead and eliminate that line. And so the conclusion is how well you achieve academically does not influence how well you perform on the job. But then someone else comes along and says, think about repetitive tasks. Some jobs have many repetitive tasks, and those repetitive tasks can influence job performance. The fact that you're doing the same thing over and over and over again can influence job performance, as opposed to you never do the same thing over and over. You have a job in which you have a lot of creativity that needs to come into the job. Well, is that somehow related to academic achievement? That is, if you have high academic achievement, might that influence the amount of repetition that there is in your job? Absolutely, it might. And so the fact that this repetition variable is related to both of these could, in fact, mask the relationship between academic achievement and job performance. Let's do another example. This time, let's go ahead and use R to help with that example. I'm going to use ice cream data. That sounds like a good thing to me. So the variables we're going to have in the data set include the consumption of ice cream per person in pints, the average family income per week in US dollars, the price of ice cream per pint, and the temperature, the average temperature in degrees Fahrenheit. Now, the data were collected in the early 50s, and as soon as we look at the data, you'll know that they were collected in the early 50s. So let's go ahead and take a look at that. I'm going to load the ice cream data. Let me go ahead and clear this window over here. Try that again. Load the ice cream data. And let's see. Let me go ahead and clear this and do it one more time. All right. Now, there are the ice cream data. Notice the income per week, $78 per week. Notice the price of a pint of ice cream. I'm on row 1 here, 27 cents. Row 2, income $79 per week, 28 cents for a pint of ice cream. If I was paying 27 or 28 cents per pint of ice cream, I would be eating a lot more warm apple pie, because to me, ice cream really needs a medium like warm apple pie in order to have the full effect. So I would be doing that. So it's probably a good thing that ice cream is not 27 cents a pint, or I might have to exercise even more than I do or suffer the consequences. So let's go back here and look now at the correlations among all these variables. And I want you to pay special attention to the correlation of income and consumption. You see it right here? For all practical purposes, they're not correlated. Now that's kind of surprising. If I was going to build a model in which I had income and ice cream consumption both in the model, I would propose that the higher the income, the more you might consume. Now, others might argue, well, if you have higher income, you might have higher education level, and the higher education level might teach you that you probably shouldn't consume that much ice cream. So there's a lot of different arguments one can theoretically make. And if you're thinking about modeling on the basis of theory, I applaud you, because that's always the way we should do it. But for this example, let's just look on the surface at the fact that income doesn't seem to make a difference. Now, if you think about the early 50s and making the kind of money that people were making, even though ice cream was not very costly, for some families, it might be a big deal to think about going out and buying a couple pints of ice cream, and you wouldn't want to do it that often. So let's find out what's going on. Is consumption and income really unrelated to each other? Here's the model. And the results should not surprise you. Very, very little effect here. Notice that coefficient, how small it is. Very little effect. What was the consumption variable here? Ice cream per person in pints. And I don't know if that is for a week or what that is. I really, the code book needs to be better. It needs to tell me over what period of time, but I think this is the best I was able to do based on the information I had from the study that's referenced up here. So let's go back to our notebook, and we see this is that for every single unit of income, we actually increased the consumption by 0.0005 pints, hardly any at all, for every dollar increase in your weekly income. We hardly changed it at all. And so you're getting a correlation, a multiple R squared that's basically 0. You're getting a P statistic that's very large. All right, we might be tempted to just go ahead and throw consumption out of the model, but not so fast. Note the influence of income when it is modeled with temperature. So both temperature and income are now in this next model. Now all of a sudden, the effect went from 0.0005 to 0.003, which might seem rather small still, but notice the p-statistic. This is an actual, a stable estimate. We believe that it's non-zero. We believe that there is some effect. The total effect overall, with income and temperature both in, is 70% of the variation in consumption can be explained with income and temperature. Let's take it a little bit further. Let's analyze this effect by looking at the correlation for income and consumption once controlling for temperature. So I am going to regress consumption on temperature. I'm going to regress income on temperature. What does that do? That takes the effect of temperature out of both of them. So when I look at the residuals, I'll be looking at the relationship of income and consumption when controlling for temperature. And there it is. Notice the correlation, 0.50. Remember what the correlation back here was? 0.05. We went from a correlation of 0.05 to a correlation of 0.50, and indeed stated that 25%, a full 1/4 of the variation in consumption, can be explained by income. What happened? How did that happen? Well, let's go back up and look at one more thing in our correlation table. Look at the correlation of temperature and income. It is not negligible. It is minus 0.32. Higher the temperature, lower income. In the early 50s, when these data were taken from all over the United States, if you went south, your income level went down and the temperature went up. And so this relationship of temperature to income from these data that were collected, that actually helped to suppress the relationship of income to consumption because temperature was also related to income. Other variables might be related as well and also contribute to the suppression, but this is an example of suppression where you have a correlation of 0.5 that's reduced to a correlation of 0.05, actually near zero.